We're going to start our discussion of the four different pathways involved in substitution and elimination reactions by looking at SN2. So let's start by looking at the label SN2 itself. So in this label, the S stands for substitution. The N refers to nucleophilic. And the 2 means bimolecular. Now, this is a term from kinetics, and what it means is that there are two chemical species involved at the rate determining step for the reaction. Okay, so that's a bimolecular reaction. So SN2 is bimolecular nucleophilic substitution. So let's look at the example shown here. Now this example is shown twice. We're just writing it in different ways so that you can get used to seeing again how organic reactions are presented. So in the first line, the ethyl bromide, this is our substrate or electrophile. It's going to react with the hydroxide ion, which will act as a nucleophile. The bromine, as we've seen in other examples, is going to play the role of the leaving group. Which I'll abbreviate as Lg in the examples that we'll give. Now, the same reaction is written out in this form, directly below. So ethyl bromide is going to react with sodium hydroxide with water as the solvent to give you ethanol as the product. So in this case, water is acting as a solvent. Now remember that the nucleophile is something that has electron density that it uses to form a bond to something else, and that something else is the electrophile. So oftentimes the nucleophile, although not always, but oftentimes it's going to have a negative charge. So as we can see here, when the nucleophile has a negative charge, that is to say when it's an anion, the way that we get it into solution is in the form of its metal salt. So when the nucleophile is an anion, it is introduced to the reaction as a metal salt. So in other words, a cation and an anion. Let's draw the mechanism for how this happens. We know it's SN2, which means that it's a concerted reaction mechanism, which means that the substitution is taking place all at once in one elementary step. So the hydroxide ion attacks the carbon with the leaving group and pushes the leaving group out. So in the result, we get ethanol and the bromide ion, which departed the molecule. Now notice in all of these examples, including the mechanism, well, actually not all of the examples. In the second example, the one that I've circled, it shows that the hydroxide goes into solution as sodium hydroxide, although we know that's going to split apart into ions in water. But up above, in the first line, and where I just drew the mechanism, notice that I omitted the sodium. So in your book, probably in the mechanisms, they'll include the counter ions, the spectator ions, which you can do if you want to. But what I've noticed is that sometimes they can confuse people, and people see the spectator and they want to use it. They want it to do something, even though it's a spectator. They don't want to just have it in there. So I would say you can omit spectators from your mechanisms. We know they're in there. We know that all charge has to be balanced. And so if you can take that on faith, then it's okay to leave them out of your mechanisms. You don't have to include them. Let's look into the details of what's happening at the transition state for this one-step reaction. So in the transition state, what's going on is the following in this example. You have a hydroxide ion that's forming a bond to a carbon, and at the same time that that's happening, the bond between that same carbon and the bromine is breaking. That carbon is also attached to a pair of hydrogens and to a methyl group. The hydroxide ion on the oxygen, there's partial negative charge, and there's partial negative charge building up on the bromine. The bonds that I've drawn with these dashed lines represent bonds that are forming and breaking. So remember, that's what characterizes a transition state. It has at least one bond that's not fully formed. So our highlighted bonds are forming or breaking. So what you have then is a carbon that essentially has 5 things around it. So we call it a pentacoordinate transition state. Because of the developing charge, those 2 partial negative charges, and the fact that there's crowding around that carbon, because you have so many things around it, those 2 factors are responsible for the higher energy of the transition state. Now the rate of the reaction. For an SN2 reaction, remember this is bimolecular. So the rate is going to depend on the concentration of 2 species. So the rate law for an SN2 reaction is that the rate is equal to the rate constant K times the concentration of the nucleophile times the concentration of the electrophile. In the present example, it would be K times the concentration of hydroxide, which is the nucleophile, times the concentration of ethyl bromide, which is the electrophile. So each of these concentrations, because there's no superscript, there's no exponent, is raised to the first power. So when you add the powers together, 1 and 1, you get 2. And this is what tells you that the reaction is second order overall or bimolecular. When we talked about addition reactions, for some of those, we focused on the stereochemical outcome of the reaction because the stereochemical outcomes were specific to some of these addition reactions. The SN2 reaction, as we actually already saw, also has a particular stereochemical outcome. Now, this is called an inversion of configuration. So what we saw when we encountered the SN2 reaction as a step in an addition reaction mechanism was that when a nucleophile approaches a carbon, it approaches it opposite the bond to the leaving group. This is referred to as a backside attack or a backside approach. So the nucleophile in an SN2 reaction always comes in and attacks the carbon on the other side from where the bond to the leaving group is. Now, as a consequence of this, if the carbon that's getting attacked is an asymmetric carbon, meaning again that it has 4 different groups attached to it, and if the nucleophile and the leaving group have the same priority, which is most likely the case, but not always, then the result is going to be an inversion of the configuration at that asymmetric carbon. Let's look at a general example, and then we'll look at a specific example. So here's an electrophilic carbon that has a leaving group attached to it. I've labeled it with a star, and I've just arbitrarily labeled the groups surrounding it with their priorities. So let's say that the leaving group has the first priority, whatever A is has second priority, and what B is, that has third priority. The hydrogen, which has the lowest priority, is already going back. So when we assign the configuration here, we see that it's S. Now a nucleophile comes in and attacks this. As the nucleophile attacks this, A and B and the hydrogen are all going to move away to get out of the way. The result is the inversion of configuration. So now, assuming that the nucleophile and the leaving group have the same priority, so they're both first priority in this example, and the other two groups, A and B, still retain second and third priorities, now when we assign the configuration, we see that it is R. So the configuration has inverted. Okay, now let's look at this again with an actual example. So let's say that it's the hydroxide ion that's reacting with R2-chlorobutane. Now, as an aside, you should look at this structure carefully and see why this is R2-chlorobutane. So make sure that you track with the number of carbons that's in that structure, that this is a butane, that the chlorine is coming off of the number 2 position, and that this does have an R configuration. So verify all those things, pause the video, verify those things before we go on. Once you've done that, let's take a look at the transition state. So the transition state is going to look much like we saw on the previous page. So a hydroxide ion attacking a carbon that has a chlorine attached to it. Chlorine has a methyl group, hydrogen, and an ethyl group. So as the hydroxide comes in, it comes in opposite the bond to the chlorine, so opposite this bond here. And these three groups are going to move forward as the hydroxide approaches. The result, as shown on the far right, is an inversion of configuration. So pause the video again and come up with a name for this compound that includes the stereochemical designation of R or S. Once you've done that, you should come up with S2-butanol as the name of the compound. Now what we're interested in next is why the nucleophile approaches opposite the carbon-leaving group bond. To understand that, we have to understand what's going on with the orbitals, the HOMO and the LUMO, in the reaction. So if it's the reaction of hydroxide ion with R2-chlorobutane, let's assign the HOMO and the LUMO. So the HOMO is going to be in the nucleophile, as we've seen previously. And in this case, we can think of it as either a non-bonding molecular orbital, or we can just call it an sp3. Either way, what we're looking at is what is the orbital that contains the lone pair that's doing the attacking. Okay, so the HOMO is an sp3 orbital. So let's, down below, draw a picture of that. So here's an sp3. On the hydroxide ion. And it's going to have a pair of electrons in it. Now for the LUMO, remember that the question we ask when we look at these reactions is, did a bond break in the electrophile? And the answer is yes, it did. It was the carbon-chlorine sigma bond that broke. That means that the LUMO is the carbon-chlorine sigma star. So remember, it's always the anti-bonding orbital that's the LUMO if a bond is breaking in the reaction. Okay, so let's take that information and go down to this diagram. What I've drawn here is the carbon-chlorine sigma star orbital. So this whole picture is that orbital. Now, as you can see, It's a kind of a complicated orbital. It has various parts. There's various lobes. We've got some nodes going on in there. Notice that there is at least one of those nodes is between the carbon and the chlorine. So you have a node in between the two nuclei that are trying to bond to one another. That's kind of a hallmark of an antibonding orbital. So that's one of the nodes. But this is what the orbital looks like. So when we think of these two orbitals coming together, we can imagine that there's three general ways that they might do this. Okay, so one of them could be that the sp3 orbital comes in right between the carbon and the chlorine, like so. In that case, it's going to have constructive interference with one of the lobes. So you'll have bonding possible over here, but on the other side, these are out of phase. And so there's no net bonding possible if it approaches in between the two nuclei. It could also approach on the other side over here, where the chlorine is. The problem with that approach primarily has to do with electron-electron repulsions. So remember, the hydroxide ion has 3 lone pairs, and so does that chlorine atom. And so the electron-electron repulsions are not going to be a favorable way to get the hydroxide ion to react with this species. Another thing is that the extent of overlap is not as great as it could be. Because what we're looking at is one of the smaller lobes of the carbon-chlorine sigma star orbital. So the sp3 orbital is going to find a better place to overlap, and that's going to be on the other side. So I'm going to draw another version of the sp3 orbital that just has the shading reversed. Oops, I didn't have the shading reversed. So that we can see that there's much more efficient overlap So this is the best overlap possible between the HOMO and the LUMO. Because of that, this is the preferred trajectory of approach. So this is another thing that understanding a little bit, even just a little bit about molecular orbitals can tell us is why we get the stereochemical outcomes we do. Primarily, it's because of things like this. Where is the best overlap between the reacting orbitals? What's the best energy match between the reacting orbitals? So this is the preferred trajectory of approach. Okay, so what does this mean in terms of us drawing products? Well, we've already had some practice doing this, again, in the context of the SN2 step, when we opened a bromonium ion, for example. But let's try this again with some new reactions. Let's draw some products, taking into account the stereochemical outcome. So when you draw an SN2 reaction, once you've determined that your conditions are going to give you primarily an SN2 pathway, when you draw the product, you must remember the stereochemical outcome. So we're going to look at a couple of reactions, and we're going to use this not only as a way to learn some things about drawing these products, but also as a way to get into the routine of how we would assess each of the components of the reaction mixture. So let's start by looking at our substrate. So the question we would ask is, what kind of substrate do we have? Now remember, that's dictated by what kind of a carbon the leaving group is attached to. That's a secondary carbon. So we have a secondary substrate. We've already seen in a lot of the examples so far, bromine as a leaving group. Now we know that the bromide ion is very weakly basic, so this is going to make bromine a very good leaving group. So we have a good leaving group on this. Now we have sodium cyanide. Now, again, you can disregard the counter ion. So we're just looking at Cn minus. So what kind of a nucleophile is Cn minus? So to answer that question, let's go back to the reference tables on the second page. And let's find the cyanide ion on this table of frequently encountered nucleophiles. And what we see is that it's in the good category. So we have a good nucleophile. So our nucleophile, which is the cyanide ion, is a good nucleophile. So we can identify those features. Now this thing over here that's underneath the arrow, DMSO, this is a solvent that's frequently used in SN2 reactions. We'll say more about that later on. Okay, so the cyanide ion, let's draw a mechanism for this. Cyanide ion reacts through its carbon atom, and so it's going to attack the electrophile. It's going to attack the carbon that has the leaving group, and the leaving group is going to get pushed out. Now remember, it's an SN2 reaction. This is all happening at the same time, and the cyanide ion is coming in opposite the bond to the bromine. From our perspective, the bromine is going back. That means that the cyanide ion is coming from the front, again, from our perspective. And so when you draw the product, you're going to draw the cyanide, or the nitrile group, with a wedge, because it came in from the front face, or the front side, I should say. And then the methyl group on the lower left was not involved in the reaction, so nothing happens to its stereochemistry. And of course you have your bromide ion hanging around there as well. Now one thing I would point out here is that this is an example of what we would consider a successful SN2 reaction. And by that, I mean that it's energetically favorable. Or exothermic. So this is a successful SN2 reaction because something that was more strongly basic replaced something that was more weakly basic. So something more strongly basic replaced something that's more weakly basic. Now notice that neither of these things, okay, the more strongly basic thing was the cyanide ion, the more weakly basic thing was the bromide ion. In this reaction, neither one of these is acting as a base, but we can use their base strengths to understand energetically what's happening in the reaction. Let's look at another one. So let's look at this substrate. So we have an alcohol here. What kind of alcohol is this? Primary, secondary, or tertiary? If you said secondary, you're absolutely correct. Now let's take a look. The only thing here that we might think would detach and become a leaving group is the OH group. But we know that if it got kicked out, it would leave as the hydroxide ion. Because remember, the leaving group takes the pair of electrons that joins it in a bond to the carbon that it's attached to. Hydroxide is a strong base, and so it's a very poor leaving group. So what we have going on here is a poor leaving group, meaning that no substitution or elimination reaction can take place until we do something about that. Fortunately, we have ways that we're going to look into in more detail later in this packet to make the OH group a better leaving group. And one of the ways is to turn it into something called OTS. Again, we'll look at details later. This is still a secondary substrate, but now, instead of the poor leaving group, we have a great leaving group in OTS. So now we can do a reaction. And because we're talking about SN2 reactions, we should do an SN2 reaction. So we have KN3. KN3 is potassium azide. So that's its name. The K part you know, that's the counter ion. And so we don't need to consider it. All we need to consider is N3 minus. So N3 minus is the azide ion. So take a minute, go back to the tables on page 2, and find out what kind of a nucleophile the azide ion is. Once you've done that, hopefully what you learned is that it is a good nucleophile, so it's in the good category. And so we have that going for us as well. For the azide ion itself, I'd recommend that you draw a Lewis structure for this. That's good practice, because this is a kind of a weird Lewis structure. So that'll be a good thing to try. Okay, and then finally, down below the arrow here, we have this thing called DMF. This is another solvent often used in SN2 reactions. Okay, so what's going to happen? The azide ion is going to attack this compound. So this one here, it's going to attack this compound at the carbon and displace OTS. But the OTS group is coming forward from our perspective. And because the azide ion has to attack from the back, that means that when you draw the product, the bond to N3 will be directed back as a dashed line.